I want to thank the International Linear Algebra Society and the organizers of this conference for giving us the chance to talk about our work. This is work with Anna Davis of Ohio Dominican, and I'll be speaking about the eigenvalues of matrices with common Gershgorin regions. A quick overview. We're going to define some sets we call eigenvalue orbits and eigenvalue trajectories. We will be talking about special points because these are both, turns out, algebraic curves. And we'll be talking about zeros and poles and also singularities of those curves. After that, we'll shift and talk about foci of those algebraic curves, and then we'll have an application to the eigenvalues of equimodular sets. Now, Gershgorin proved his theorem in 1931, and most of you should be familiar with this. It says that the eigenvalues of this 3 by 3 matrix must appear somewhere in this region, the union of these three circles. The circles have centers that are at the diagonal entry of the matrix, and the radius is the sum of the absolute values. So this last one, 0 plus 1, has a radius of 1. My red circle is centered at 2 with a radius of 1. I've placed that in red because shortly I'm going to replace that with a variable, and we can change the radius of, say, one of the entries. If you'd like to learn more about Gershgorin's theorem, I highly recommend Varga's book, Gershgorin and His Circles. A great read. Okay, so I want to define eigenvalue orbits and eigenvalue trajectories. So as I said, we're going to replace one off-diagonal entry with a variable of the form r e to the ti. And so there's two things I can do here. Now, if you think about what happens when I make this variable, as long as I fix r, I don't change the Gershgorin region. The centers of each Gershgorin circle are certainly the same. The radii of most of the circles is the same. The only one that could change is this, but if I fix r, that modulus is the same, and so it has the same Gershgorin region. And so we're going to consider fixing r and varying t. And as I vary t from 0 to 2 pi, I generate something we will call an eigenvalue orbit. Now, if we're going to play this game, we can do the same idea, but fix t. So let's fix an angle and vary r. That, of course, will vary one of the disks. The red disk in the picture may be changing radius. But we'll call the shape, the set of all eigenvalues, an eigenvalue trajectory. So here's that 3 by 3 matrix where I replace the 1 with r e to the ti. And I like to tell people, start with r equals 0. Let's think about what it looks like. So then we know we have an eigenvalue at 2, which is right here. If you examine the upper left corner, you'll discover that the other two eigenvalues are at plus or minus I, which are here and here. So now if we set r equal to 1 and vary t from 0 to 2 pi, we get these small little ovular curves. This is the set of those eigenvalues as t varies, and they're around each of the r equals 0 eigenvalues. Now if you set r equal to 2, by this point these curves have blended together and become a single eigenvalue orbit, a single component. This is r equals 5, this is r equals 6. And I also graphed one trajectory. This is when you set t equal to pi over 3, and of course it's going to go through, this curve is going to go through each of the r equals 0 eigenvalues because we're varying r. But this is the shape that we get. So I would like to come up with an equation for these things. This is the characteristic equation, which is computed by expanding along either the row or the column containing the variable entry. And when you do that, you get a p of lambda term plus another polynomial I'll call d of lambda, which is times the variable. P of lambda is going to be degree n. D of lambda will be a smaller degree. I'll call it m. And what we know is that m will be less than or equal to degree n minus 2. So my first theorem is that using this form we get a equation of our algebraic curve. It's a polynomial of degree 2n is the equation of the eigenvalue orbit. Let's take a look at the 2 by 2 case where the variable is this corner. Notice when r is 0, you'd have 0 eigenvalues of 1 and -1. And when you increase r, you get these ovals of Cassini. The very special case when r equals 1, you have this singularity in the middle, and that's called the lemniscate of Bernoulli. There's a picture like this in Varga's book if you want to look at that. So the next theorem is the equation for a trajectory. It turns out it's also a polynomial. It's degree n plus m, where again m is at most n minus 2. In the case of the 2 by 2 matrices, I've now graphed the trajectories. Since 2 times 2 is 4, minus 2 is 2, these degree 2 curves, which are the trajectories, are hyperbola. And the hyperbolas go right through these 0 eigenvalues. And these eigenvalue orbits, the ovals of Cassini, were degree 4. Okay, time to consider special points. We already talked about the r equals 0 eigenvalues. But if we write the characteristic equation for this matrix C in that form, p of lambda plus d of lambda r e to the ti, and then if we solve for r e to the ti, we get a function of lambda, which is a rational function. So the zeros of f of lambda, of course, are the 0 eigenvalues, but the zeros of the denominator d of lambda are also important. Those are poles of this rational function. In this example, 1 minus I is a pole, and you can see that right here. It'll actually be on the trajectory. And if I take the same matrix and graph lots of orbits and lots of trajectories, one thing you'll notice is that each trajectory heads right for that pole. And so we have a theorem that every trajectory contains every 0 eigenvalue and every pole. If you asked yourself when you looked at my pictures whether this is an orthogonal family of curves, that answer is yes. Eigenvalue orbits and eigenvalue trajectories are orthogonal. So I mentioned that we want to find singularities. We're going to take the derivative of this function and set it equal to 0, and we can find values of r that will give us singularities. In this 5 by 5 example, I've highlighted the orbits and the places where we have singularities for certain orbits. All right, let's move on to foci. Why foci, you may ask? Well, before I studied Gershgorin disks, I studied the numerical range quite a bit. And most of you are probably familiar with it. It's another eigenvalue inclusion set. Kippenhahn in 1951 proved that it is the convex hull of a certain algebraic curve. And it's easy to see that the numerical range contains the eigenvalues, right? You can substitute a lambda x where that ax was, and it works just fine. But not only is there containment, but the relationship to the algebraic curve is interesting. In fact, the foci of that boundary generating curve that Kippenhahn found are the eigenvalues. So here's the relationship between geometry and linear algebra coming at us. Now what are we doing? We're finding foci of eigenvalue orbits and trajectories, so I claim we're finding foci of the foci. In order to do this, to talk about foci, we need to work in the world of CP2, and I'll identify xy with xyw, its homogeneous coordinates. When you do this, these points, 1 negative I 0 and 1 I 0, are called the circular points at infinity. And my definition of an ordinary focus is take a tangent to the algebraic curve from I and from J, from these two circular points, and see where they intersect. That intersection point is called a focus. Now, back to here, the picture. Sometimes the curve can actually pass through the circular points. When that happens, if we do the same thing, we get what's called a singular focus. Well, it turns out that eigenvalue orbits and eigenvalue trajectories are both what are called circular curves. And what that means is they will have singular foci. So we need to look for both types of foci when we study these eigenvalue orbits and trajectories. To find them, we're going to employ methods that were used by Wampler in this paper in 2004. And Plücher's formula can tell us how many foci we should expect to find. Now, where do we find them? Well, here's a 3 by 3 matrix, and I have a picture of all the foci over on the right. It turns out the singular foci will be right at the r equals 0 eigenvalues. So this is an orbit of r equals 2. It has those as its singular foci. But any orbit will have those as singular foci. Take a very small value of r, and those will be singular foci. The red points will move, but the black will not if you vary r. Now, the red points are my ordinary foci. Where are they? They lie on trajectories that pass through singularities of orbits. Here's an example. I drew an orbit. It looks a bit like a cardioid, but it has a little curve here and a singularity. Then I drew a trajectory through that singularity, and you'll notice that this trajectory passes through 3 of the red ordinary foci in that picture. The other 2 sets of 3 ordinary foci lie on 2 other orbits that have singularities. They lie on trajectories passing through those singularities. What about foci of trajectories, you may ask? It turns out that the singular foci of trajectories are at the poles. So that's kind of neat, right? This picture before, we had a pole at 1 minus I. That is a singular focus for every trajectory of this matrix, eigenvalue trajectory. And the ordinary foci of trajectories lie on orbits containing singularities. So that's really neat too. Take a hyperbola, which is a trajectory for the 2 by 2 case, ask where are its 2 foci? The answer? They're on the lemniscate of Bernoulli, because that's the oval of Cassini that has the singularity. Quick application to eigenvalues of equimodular sets. This is what Varga calls omega of A. It's a set of matrices that have the same diagonal elements as A, and the moduli agree. So in other words, each matrix in omega A will have the same Gershgorin region that A does. Varga was interested in the set of all eigenvalues of this equimodular set. And so for this matrix A, here's a plot of 3,000 eigenvalues, right? Take 1,000 different matrices that have the same Gershgorin region, plot their eigenvalues, and notice there are clearly some internal boundaries to this set. And Varga found that very interesting. He used he proved that they were the intersection of minimal Gershgorin sets. Well, what we're able to do is, if I replace the 1s with some random theta 1, theta 2, theta 3, these e to the theta i's, I don't change the Gershgorin region at all. I'm still in the equimodular set. And here I will put my r e to the ti, r is 1. And I'll compute the orbit by varying this t value. And that gives me, if I do this 50 different times, 50 different theta values, triplets of theta, I get this picture here on the left, which is pretty good. If instead I move e to the ti down here and put an e to the theta I here, I get this picture here on the right. So we studied eigenvalue orbits and eigenvalue trajectories. They're orthogonal families of curves. The zeros and poles are singular foci of those curves, and every eigenvalue trajectory intersects each of these points. The orbits with singularities end up being ordinary foci of trajectories. Trajectories through those singularities are foci of orbits. And finally, orbits are subsets of eigenvalues of equimodular sets, and so we think there's an application there. I want to thank you for your attention. I have references here for you, and you can email me here if you have any questions. I think there'll be time for questions now, too.